Good morning, everybody. So today we will present lecture 2. As we mentioned in lecture 1, so the last page we have an N-type material and we have P-type. So this is one the acceptor and the other one is a donor. So we say we will join these two materials so we can get a diode. So the diode, semiconductor diode. So the diode is a diode constructed by a joining N-type and P-type material together. As an instance, so the two material joined by, and they have joined with the electrons, holes and holes regions, and joined with the combining. That's mean. And there is an it will be there is with the two P and N, there is a depletion region. This depletion region resulting in a lake. So lake, it means this one, and it is a lake of carriers in a region near the joining. So near the joining depletion region, we will call it, there is a lake of carriers. So there is no carriers will be moved here. It's not no, it is just a difficult to moving. So that means that the current, it will be so difficult to move through this depletion region. So when the depletion region is bigger, it will be impossible, or it will be not easy to move. There is a current, and when the depletion region is small, it will be impossible to move, or there is a current. We will see now. If there is nothing will be joining, like here there's nothing voltage or supply or applying anything, the diode, it will be normal, no voltage, no current. That means 0 volts, 0 current. That's it, stable. If we want to get like a circuit or to activate this material, we will plus pulses or we will apply voltage. So apply a supply, something like for example DC supply or AC supply, whatever. When we applying voltage supply, so when there is a voltage, there will be a current. So the current will be through the diode. If the depletion region, as we say, it is a small region, if that means this type is forward bias conduction. That means V diode is bigger than 0 volt. Let's see. So the diode in this case, there's through current. Forward bias, it will be when a positive voltage with the P type. P, positive. So P type, we say it's positive. There is a holes more than the electrons. And positive with positive, that means forward bias, and negative with the negative. I want you to memorize this figure, this the shape for diode, forward, and this is the contacts. Let's take opposite this configuration. It will call the reverse bias conduction. That means V diode is smaller than 0 volt. Why it will be like that? Because if we connected an opposite negative with P, so there will be current through, absolutely it will be through from here. So it will be opposite opposite with N. That means the depletion region will be bigger, and it will be not impossible, but it is very difficult to move the electrons and uh, a good current. And here in real, the current, it will be smaller than 0.000, and it will be nano ampere or nano ampere or micro ampere, nano ampere. So it is the current is saturation current. Also, I want this one. So we will apply these with the examples. Now, if we want to drawing these characteristics for forward and reverse, there is a figure for plotting figure with voltage current in engineering. So if we want to do it as an engineering figure characteristics, let's take it. If it is, so this one is a forward and this one is a reverse current. Why? Because if we apply, how can we get this figure? If we apply voltage 0.1, 0.5, whatever is bigger, we will get volt current. So in experiment, we will take a diode and we will take a voltmeter. So we will scale whatever voltage, it will be what the magnitude for current. That will be forward current and forward voltage. Also, we will opposite the supply. Then we will scale how much it will be volt current voltage. We will get in ohmmeter the scale for current. Then we will draw. So this is the characteristic, and at the end we will get the characteristics for this one, for diode in reverse and forward. Now, and here we will name it as a breakdown region for this one, breakdown, and here potential 0.7. As we say, 0.7 for germanium and 0.3 for silicon. This threshold voltage. This is the comparing between, not the comparing, when it is for mathematic equations. It will take I diode with I saturation. That means I forward with I reverse saturation. So there's a combination between two of them, and they take it with a definition and the revision. They do it and they get this equation. So I want to memorize this one, and this is the K kinematic and for germanium, and also we have K a constant, temperature, that's it. Now for germanium and silicon, just I say magnitude for the region or threshold 0.7 and 3. That's it. Just look to this one. Nothing. We need just memorize this one. Threshold. There is the temperature. It will be affected the diode and the working with the diode. That's me. How come? If we maximize the temperature, for example, if the temperature for the room that working with a diode 10 degree, the current, it will be so small, it will be 1 microfarad and 2 microampere. Then, if they change the temperature, it will be high, 25 degree. The current, it will be more, then increase. Also, if we increases until 100, it will be 0 milliampere, or it will be more than this one. Okay, so that's mean if we have a increasing temperature, it will be increase the current for the diode. Also, we have a maximum power dissipation. This is the equation for maximum power. You know the power and you know the maximum power. So V diode multiplied by I diode, I will get the power dissipation. We have also some, if we want, for the first lecture, we have a resistivity. It will resistivity equal resistance multiplied by area for material, also divided by the length of the material. Now, that's mean the R resistance, it is with the Ohm's law, it is connection. There is a connection between voltage and the current with the resistance. That means always we want to get a connection between the input and the current applied. This is the connection between it. It's always we do it as a Ohm's law or resistance. So whatever, we always want to get a resistance. So the applying of the DC voltage here to a circuit containing a semiconductor diode will result on operating point of characteristic curve that will not change with the time. The resistance of the diode at the operating point can be found simply by finding the corresponding level of V diode and I diode. That means we have corresponding V diode. Now, let's have resistance levels. We have 3 types of resistance. First one, DC direct current or static resistance. This is the curve for if we have a diode and we take it to the VDC, and this is the diode. Okay, so VDC, we get V diode, and this is I diode. Okay, so V diode, I diode when we have applying VDC. We get the curve for specific point. It will be taken a vertical straight line to the current axis. Then we get the point that we wanted for I diode here, and we take a vertical here. Okay, and we will take this is the horizontal or whatever. This is point VD, horizontal and vertical. Okay, so VD, we have this one point, specific point, and ID, specific point. Nothing change. It is fixed. We will get 2 points for diode for voltage and current. We will calculating resistance. Example 1, the same that we take it and we mentioned before. The second resistance is AC diode. So the AC diode, when we apply what? When we apply alternating current or voltage. So this one, VAC. Okay, so VAC, when we applying alternative current, we will get, if you memorizing when I plotting this figure in a whiteboard in university, so I say there's a point, every point, so this is the sine wave, every point it will be junction in time. So that means moving the instantaneous operating point up and down region. And this one, it will be not fixed point, one point. So we have up and down because it is changing with time. Alternative current changing with time. That means we get a curve, not straight line. This curve will take a junction or joining point to get rectangular, this rectangular, and we will calculating changing from here up to here. Okay, let's see the example. This is so it's changing. This one is that's mean changing in voltage and changing in current. Let's take this example. Let's take the first one. He said determine AC resistance at ID diode 2 milliampere. So this is 2 ampere milli, so on. Let's take 2. So this one is a 2. I will give you in a test this one. I'll give you the curve, then you will applying just the straight line, this one. We'll take it and you will get the point, Q point. So this one is a Q point. Okay, so the Q point, this one is a Q point. Now, junction with the H, we'll get straight line. We will take straight line up and down, up and down the I diode 2 ampere, up and down. For example, here down it will take with the x-axis 0. Here's the 0 ampere because it's 0, and here from here to here, this point, it's 2. So I will take 2 also because we take this conjunction or the curve that's aged, the curve, the Q point, the curve tangent to the curve through the Q point, straight line down tangent to the curve. So this one is tangent. Now up also we will take 2 ampere, so 2 up to 2 it will be 4. Now I will take this point, so from this point until this point we will work with this one. So from you will get ID 4 milliampere minus 0 milliampere 4 milli. The voltage here, how much? I will take it, I will calculate it. So 4 ampere straight line, I will take the point here for voltage. Also here, how much? The 0.65 or something. Okay, so the up 0.76, this one, minus 0.65, this one, okay? And we will get the division or d delta Vd 0.0. Now we will get R resistance Vd over. The same thing for the others, just until this one, okay? No need this part, I don't need it. Now the third one, the last one, is average AC. Average AC resistance, if the point signal is sufficiently large to produce a board swing such as indicated here, thus means the resistance associated with the device for this region is called average AC resistance. What does it mean? That means if we have a curve and it is more large than we can get the tangent, and he say it is bigger, so this one is more bigger than we get it, he will give me I will get the average resistance. We will get you will have this in the test. We will give you the figure and we say determined as an average resistance. So peak up, you will get this one, up and down. So up and down from here to here, you will calculate the ID. And then when you centered the point for V diode, and up also we will center it here, we will get V diode. So the resistance, it will go to V resistance, average resistance. Thank you for this lecture, and I want to give me next week the homework one. Solve like the 3 examples that we have it over this lecture with the new values that everyone assuming them alone. So everyone put any values you get, any values here, for example 20, 21, 5, put any values and you calculate it and determine everything like the examples. Thank you for today.